Yes.
Excellent. Well, thanks, Mitch. So good afternoon, everyone. As I've been introduced, my name's Chris Drummond and I work at the University of New South Wales Water Research Lab. And today I'll be talking about kind of the different ends of the spectrum when it comes to coastal monitoring techniques to understand the beach and the business of the beach through smart cameras. And this is this body of work that I'll present today is not just from one person. This has been a very large collaborative effort from a number of different people, some of whom are here today, including Dr. Mitch Harley, my colleague Matt Blacker. For the machine learning side of things, I had a lot of assistance from Annie Zhu Wang from the university as well, and Dr. Rip as well, Dr. Rob Brander, and many others as well have contributed to the work that you'll see today. The photo you can see there right now is it's quite nice that both of the 100-second presentations this morning were focusing on the Gold Coast, because that's a great photo there of some of our camera systems up at Surfers Paradise on the Gold Coast, and that's kind of where I'll start my presentation and then jump into some of the other systems we've been using. So it's just a bit of an overview of my presentation today. I'll talk about some of the coastal monitoring that we do up on the Gold Coast to serve as an example of a very sophisticated network of what you can do with cameras. And then I'll introduce a much lower cost camera system that we've made a few compromises on what it can do in order to bring the cost down and make it a lot more flexible. And through that system, I'll talk about some use of machine learning for people counting, just like the example you can see there at my home break at McMaster's Beach, where we've been using the low-cost cameras to understand beach usage. And at the end of the presentation, I'll present a number of applications of the systems and some results. So just to serve as a bit of context about coastal imaging and monitoring the coast using cameras, today I'll be presenting two different systems that do different things in terms of understanding the coast. On the left-hand side here, we've got a very low-cost image-based monitoring system that I'm calling the Wamberal Beach Stat system, and that's very cheap. It's under $1,000 and it's very flexible because you can pop it on anything, and it's got its own power and internet connection. On the other hand, if you are able to spend a bit more money, you can move to a video-based monitoring system. And here's an example here on the right-hand side of one of our coastal imaging stations up on the Gold Coast at Drummond. And these systems generally comprise of multiple cameras that look at different parts of the beach, and they're also able to do video-based analytics. But as a result, they cost a lot more money to set up. But to start with, let's look at the Rolls-Royce solution and see what it can provide before we jump into the lower cost system. So let's talk about our Gold Coast monitoring system. As a bit of context, up the Gold Coast is on the border of Queensland and New South Wales. And on the Gold Coast, we've got a total of 10 different coastal imaging stations at these locations on the right here. And what it includes is, think of 10 high-rise buildings, and on the top of each of those high-rise buildings, we've got a bank of up to 6 cameras. And in total, our network on the Gold Coast comprises 44 different cameras. And it completely covers a stretch of 32 kilometres from Duranbar down the south here, all the way up to Stradbroke Island in the north. And this network itself is the largest coastal imaging network of its kind in the world. And it's grown from very humble beginnings. The station was first established by my colleague, Professor Ian Turner at Surfers Paradise here over 20 years ago, with lots of input from others and a huge effort from American counterparts with Rob Holman, who's in the chat right now. The system was established a very long time ago at Surfers Paradise. Since then, it's grown quite significantly and it covers this whole stretch of the coast. And what's interesting about this network is it's spread across 2 different clients. Down the south here, there's an organisation called the Tweed Sand Bypassing that's a combination of the governments from Queensland and New South Wales, and they pump sand across the border here. I won't go into a lot of details about the Tweed Sand Bypassing system, but there's plenty of information out there about it. But then the rest of the sites are managed by the local council, the City of Gold Coast, and they manage the northern half of the system. But what do one of these sites look like? To start off with, let's zoom in on the southern part of the coast here and have a look at one of the sites. So here's an aerial view of the southern part of the Gold Coast, and each one of these spots here is a high-rise building where we've got a bank of cameras. And so to zoom in, let's have a look at this one here, which is at Rainbow Bay or Snapper Rocks if you're a surfer. This break here is a very well-known surf break. So at our Rainbow Bay Snapper Rocks site, we have 4 cameras that are set up that each see a different part of the beach. And this system, we use quite expensive machine vision cameras on the right-hand side here, and they're all connected to one central computer that looks a bit like this. And each computer, it's quite sophisticated the way that we need to be able to, make sure that each site has its own power and the internet is working at each site. And it takes a hell of a lot of time to set up the infrastructure that supports these types of systems. We need to be able to remotely recycle the power on the laptops and also make sure all the cameras are working. So it takes a lot of effort to do that. If you have a look at the panorama view down the bottom here, what we can also see is what does each camera see. And here's an example here of what the different cameras are seeing at that particular location. What data products does this camera system provide us? So the first thing that we do is we collect videos. So these videos we call time accelerated videos. And every 15 minutes, we collect a 10-minute grab of videos to look at what the beach is doing. And we speed that up so that it only lasts 30 seconds, just so that you don't have to sit there and watch 10 minutes of video. The next thing that's quite common practice in coastal imaging is you take every pixel that's in a video frame over 10 or 20 minutes, and you average them to give what's known as a Timex image, which is this image on the right here. And what that does is that serves to make it very clear the boundary between the water and the land. As you can see, the shoreline is a lot more easy to see. And traditionally, to limit the amount of data that these systems transmitted, it was only the Timex images as well as some other things that were transmitted back to the processing computer back at the base for you to analyze. So these are 2 of the main data products that these camera systems provide, the 10-minute video and also the Timex image. Now let's have a chat about how we can use these camera systems to monitor the shoreline. So there's a couple of different ingredients that are required before you can extract quantifiable data from a coastal imaging site. And this revolves around the process of image rectification. If we have a look at the example up the top here, we can see 4 of the images taken from our Coolangatta site. And the first thing we need to do is we need to merge these images together. So here's an example here of a merged panorama, much like you could take on an iPhone. And once you've taken that merged image product, you can then rectify it or turn it into a bird's eye view. And this is an example here where we've gone from the panoramic view into a top-down rectified view. And the final piece of the puzzle that we need to do is we need to map the shoreline like this example here. But what are the pieces of the puzzle that we need to do this rectification process? The first thing we need to do is a camera survey. So with the image on the left here, we've got my colleague, Matt Blacker, who is assisting with a total station survey of the position of one of our cameras. So it's quite important to know quite accurately where each camera is located, because that's one of the key parts of the mathematical process to rectify the image. The second part that you need to do is you need to know where each pixel is in each image is in real world coordinates. And that involves having to get down on the beach. And here's an example here where I made Matt walk along quite a bit of the beach here at Wamberal Beach. And we took a photo every time he took a measurement. And you can see the little red boxes around where he is moving all throughout the beach as we did the beach survey at that location. And once you combine those 2 things together, you can get a rectified image. And here's the Coolangatta beach stretch that we were talking about. But if you can recall, we've got 10 different rooftop locations that are all able to do the same thing. So here's an example of 4 or 5 of our different sites. And if you then make a time-lapse video out of all of those rectified images, you can see the river of sand that we know that moves around the corner here as it's pumped out here at the Tweed Sand Bypass System and moves across to the north. So this is the type of information that's not captured using conventional survey techniques. So the image-based analysis gives us a really cool animation of sediment transport processes. All of these images are taken at mid-tide as well, so that you're not looking at any influence of the tide in the animation. So once we've done that process, we need to detect the shoreline. So there's a number of methods that have been developed over the years to detect the shoreline. Here's a slide here that I stole from Dr. Mitch Harley from his CoSnap paper about detecting the shoreline. Essentially, when you want to detect the shoreline, you exploit the differences in the color spectrum between the water and the sand. And to do that, we generally use a red minus blue as one of the methods to come up with that nice boundary, which stands out really nicely in our Timex images. And then you've got to apply an understanding about what's the water level at the time of an image. And to do that, we use a tidal forecast or measured water level, and we take into other influencing factors such as wave setup. And here's an example here where the Stockton equation has been used to account for the wave setup. So there's an example here where you look at the color spectrum between the wet pixels and the dry pixels. And Mitch has got a nice open source toolkit for the CoSnap program that detects that boundary quite nicely. But what does that look like when you've got 45 cameras? So here's one of our, here's our internal system that we use to manage our 45 cameras on the Gold Coast. This was built by my colleague, Dr. Dan Howe. And you can see as we move towards the north where we're mapping the mid-tide shoreline across 45 cameras, and we can get a snapshot of what the Gold Coast looks like at any given point in time. And because we're capturing images every 15 minutes, theoretically, we could map the shoreline every 15 minutes for a 35-kilometre stretch of the coast. This area here is where the sand backpass system is going to be popping out, looking up towards Stradbroke Island, where we're about to install another camera when the Queensland Premier lets me into the state. So we'll be able to quite nicely monitor the shorelines once sand is taken from Stradbroke Island up here and pumped down to Surfers Paradise. And then how do you present all of that data? Here's a snapshot of the portal that we provide to the City of Gold Coast, where you can have a look at the current shoreline, and we color it based on its percentile relative to long-term averages for each site. We also show them what the current shoreline looks like versus last month's and last year's. And we break up an understanding of what does the shoreline look like in different beach compartments, where we assign it a grade between A being a nice and healthy shoreline and E being quite narrow compared to historical averages. We also plot what the trend is at different locations, whether the shoreline is accreting or eroding, to provide the council with the ability to manage their coastline. You can also have a look at a time series of beach width, where as you scroll through, you can interactively see what the width of the beach is for each of the EDA lines that each of the transects that the council use to monitor the coast. So that serves to show you a bit of a spectrum as to what a really sophisticated high-end coastal imaging site can provide you. But we found that there was an appetite in the market for a much cheaper system that had some compromises on different parts of that system, but also was a lot more flexible to install. So now I'll have a bit of a chat about the low-cost WRL Beach Stat system that we've developed for low-cost coastal monitoring. So what is it? Essentially, we're repurposing trail cameras or hunting cameras, which are an off-the-shelf product that are designed to take photos of animals in the bush, but we're not so interested in that. So we've deployed them out on coastal locations. And the real benefit of these camera systems is they're low cost. They're about $700 to buy them, but they come with their own battery source. They've got a solar panel so they can operate continuously. And they've also got the location to put a Telstra SIM card in it so they can transmit the data once it's taken. And you'd be amazed that you think, oh yeah, getting power and communications for a coastal imaging site, that'd be pretty easy. But I can tell you that it is not, and it's costly and it's time consuming. And one example is when we connected our most recent site on the Gold Coast at Drummond, it took me 18 months just to get an NBN internet connection to that site. So these things take a very long time. You've got to negotiate approvals from the building managers, and it's really complicated. So this particular system removes all of that angst because it's completely portable. It's got its own power and comms, and it's still capable of taking an image every 15 minutes and a 10-second video grab that it transmits in real time. And they're really easy to install close to the action, such as on lifeguard towers. And we've been using this type of camera system as a tool to understand the economy of the coast. And here's an example here of a camera that I've hidden inside a possum box. This is at Avoca that's 5 minutes away from me on the Central Coast. And I've hidden it in a possum box so the surfers couldn't find it because I was worried they were going to vandalize it. So if any of you know the Central Coast and think they can find this particular camera, I'll give you a Mars bar as a treat because I reckon it's pretty well hidden. So when I say the business of the beach, what am I talking about? So we're able to transfer the learnings from our sophisticated coastal monitoring network on the Gold Coast and apply that to these cheap cameras using techniques such as the CoastSnap shoreline mapping technology. And we're able to look at how beaches change. Here's an example here of how a beach has receded by 37 meters in response to a storm. But we've also pushed into a new area, which is using machine learning to understand how many people are visiting different beaches. And why is that important? Certainly in the New South Wales context, we're constantly making decisions about spending money on different beaches and understanding, you know, how wide does a beach need to be in order to service the community. And one of the key bits of information that has kind of been lacking is an understanding about how many people are visiting different locations. So that introduces the use of machine learning for people counting. So the basics of object detection is that there's a couple of key ingredients, a bit like shoreline mapping, in order to detect an object in images. The first thing that you need to do is you need to annotate your data. And that essentially requires a person to sit down and manually draw boxes around something that you're interested in counting. On this example here, we've got boxes around a mask or no mask. And once you've got enough of those images, you tend to need quite a bit of them. You feed them into a model and you train it, and then you run it on an example. So a very topical example here is me being a bit of a silly bugger trying to confuse a model that can detect a mask, a no mask, or a poorly fitted mask. So I trained this one on 3 different classes. So there's an example there of me being quite silly. But we're not so interested in mask detection. So what does it mean in a beach context? So here's an example of an image taken from one of our low-cost camera systems up on the Gold Coast. This is at Wamberal Beach. And once you feed in a picture such as this, a machine learning model can give you an output that looks like this. So in this example, it's detected 47 different people in the image. It gives a bounding box around each object, and it also gives you a confidence score. If you can see here, this person, it's 78% sure it's a person, whereas this person, it's less sure. It's 36% sure that it's a person. And one of the really great points with machine learning is that there's been a significant amount of effort invested in the world for driverless cars to detect people. So you don't need to start from square one when it comes to counting people. You can adapt a number of pre-trained models that are out there in the market. And by way of example, there is a Chinese group that have spent, I think, close to a year drawing 500,000 boxes around people. So you can borrow from the learnings of those particular models. You don't need to start from square one. So a couple of things influence detection accuracy. The first thing is how big in pixels are the things you're trying to detect. In this case, people. Obviously, if a person is only 3 pixels high, it's really difficult for a machine to detect it. And that's why we struggle to use our high-rise building cameras to detect people, because they're kind of too small in pixels. The next thing that affects your detection accuracy is how big is my training data set. How many annotations did you train a model before you let it loose on a set of images? Generally, you need at least 5,000 annotations before it's good at it. And the next thing is, what is your model trained to detect? So it's pretty easy to detect people that are sitting and standing on the dry beach area. So we're pretty good at detecting that, but it's pretty difficult to detect people that are swimming or surfing in the water, just because they're really small and generally obscured. But we're making quite a bit of progress in that field. You can see an example here on the right here where we're able to detect 2 classes, which are people on the dry beach, but also the blue boxes are people out in the water. And this is an example from the Smart Beaches project, which we'll use to count people using cameras up at Newcastle, just north of Sydney. And here's some results of a breakdown throughout a day of swimmers versus people on the dry beach. But the question remains is, how accurate do you need to be? So here's a plot of manual counts in the dashed blue line versus predicted counts from the model. And you can see that, you know, the model isn't perfect at predicting the amount of people on the beach, But I like to think that it doesn't matter that you count every person with 100% accuracy. What matters to me is the trend in beach usage, which you can imagine by this idealized red line. So I'm more concerned about what are the trends in beach usage rather than 100% accuracy. If you were using people counting for driverless cars, it would be the end of the world if you missed a person because you could potentially run them over and kill them. But when you're counting people on the beach, I think you can relax your expectations a little bit. So let's have a look at a few results from our people counting around the New South Wales coast. And to do that, I'll show you 3 different locations centered around the Sydney region. And to start off with, let's have a look at Ulladulla, which is south of Sydney, about 5 hours or 4 hours. And we'll have a look at Merry Beach. So at Merry Beach, here's a picture of one of our cameras installed on a telegraph pole. And here's the view here of the beach. This is quite an interesting beach location, mainly because it's an unpatrolled beach location. There are no lifeguards at this location, but there's a very busy caravan park at the back there. And for this project, I was working with Dr. Mitch Harley and Dr. Rob Brander, looking at beach safety at this location, mainly because there is this persistent boundary rip that hugs the northern part of the coast there. So remember that there's often a rip that hugs this part here. So for this project, we were mainly looking at counting people as one class, but we were including people in the water and on the dry beach. And to do that, we sat down and we collected 5,000 different annotations of what a person looks like and fed it into the model. And here's some results here. And we had an accuracy of about 82%, which I was pretty happy with. It was a good balance between effort of annotating objects and also getting some good results. So here was one of the busiest days that we had in the monitoring period. This was on Australia Day this year. But let's have a look at some results. If you haven't used Power BI, it's a fantastic way of interacting with data. Up the top here, we've got our plots of beach usage. At the same time, we've also got the daily maximum temperature in this yellow color here. And what you'll notice is the busiest day was the hottest day. You can also have a look at what's the busiest day of the week. And you can see the weekend was the busiest day at this location. And also what's the busiest time of day. 10 a.m. was the busiest time at this location. You can also have a look at seasonality, with January being the summer months being a lot busier than the other months. So if you can remember that persistent boundary rip that hugged the northern part of this beach, you can rectify where all your people counts are, and you're able to get heat maps of where on the beach people are visiting. And what was very interesting is that we saw that there were a lot of people that were a lot of people that were on the area of the beach very close to the rip, which has implications for beach safety. Let's move to our second beach location, which is Turrametta Beach on the Sydney's northern beaches. So this is a very curious beach. This is just to the north of Narrabeen Beach in Sydney. And you can see there's a very big difference between the summer months with the width of the beach compared to the winter months, where the storms erode the beach away and expose these rock platforms. And that has some really interesting implications for beach visitation at this site. You tend to see a squeezing of beach usage on the dry beach area that changes throughout the year. So we ran our people counting detection algorithm at this location to pull together this animation here of where people have been on the beach over a 12-month period. As you see, as we hit the winter months, the beach recedes quite significantly, and all of that beach usage is squeezed into this very small corridor up here. If I had enough time to do a PhD, I'm sure there'd be all sorts of ways of correlating beach width with beach usage that could have some useful understanding for sea level rise conditions and how beach usage might change with narrowing coastlines. But let's have a look at a similar example of beach usage. Here's a plot here where we can have a look at 12 months of beach usage, where we've also got the handy plot of daily maximum temperatures through here in the yellow. And lo and behold, we see a similar trend where the hottest day of the year was the busiest day of the year. This was in January 2020, a few days after New Year's Day, when the country was burning with a lot of smoke in the air, but still people flocked to the beach in this location. So that was the hottest day, was the busiest day. Conversely, in the winter months, the coldest days were also the time where there was the least amount of beach visitation. but it's hard to tell whether that's because of it was colder or because the beach was narrower. But yeah, it's an interesting trend nonetheless. You can also see that the busiest day of the week was the weekend. And you can also see that the busiest time of day was actually the afternoon from 1 till 3 p.m. in the afternoon, which was different to the other location that I presented. This is another site that it has no lifeguards at the location. So having an understanding of these beach usage patterns are really useful in improving beach safety if you can think about when rescue is more likely to occur because there's more people at the beach. So half of all the visits were on the weekend. 40% of all visits occurred between 1 to 3 p.m. and the hottest day was the busiest day. For our last example, let's go to Wamberal Beach on the New South Wales Central Coast, an hour north of Sydney. So in July 2020, Wamberal Beach got smashed by a large east coast low that came from an easterly direction. The beach was quite significantly eroded, and there's a number of beachfront properties there that have quite ad hoc protection in front of them. So this was a bit of a disaster for this stretch of the coast. But luckily, from a monitoring perspective, we had 2 cameras that were installed that monitored the response of this site to the storm. So if you have a look here of a time lapse, this box up here is where all the action happened. And you can see that the storms were eroded, and subsequently there was a lot of effort to stabilize that area with lots of excavators and cranes lifting in large Kiowa rock bags to protect those beachfront properties. So that's a lovely time-lapse image, but we're interested in raw data. So let's have a look at some shoreline results. So here's an example of how the beach changed directly in response to the storm. So here's 2 mid-tide shorelines before and after the storm, roughly about a week apart. And you can see that the beach receded on average of 26 meters along shore. And you can see that the maximum distance, the maximum erosion occurred at about 34 meters in reduction in beach width, and that happened about 200 meters north of this particular camera around this area here. The other thing we can do is look at how the beach recovered after that storm. So here's an example of how the width of the beach changed in the lead up to the storm. The beach then receded those 26 meters, and then you can see the very slow recovery of the beach after that event. For a final application of the camera systems, let's have a chat about rip analysis and lagoon management. So a New Zealander researcher by the name of Tom Shan developed a really easy to use MATLAB tool to look at wave breaking detection. It wasn't as, it's not as sophisticated as some other methods out there, such as our second 100-second presentation that use machine learning. This one just looks at kind of white pixels to look at where waves might be breaking. But we're able to easily apply it to a time lapse from our smart camera system. And you can start to see this intensity plot of where wave breaking is occurring. And you can see a couple of interesting things if we zoom in on this wave breaking intensity map. So using Tom's tool, you get a nice little map like this where you can have a look at areas where there is no wave breaking. So these areas here, the absence of wave breaking, you can infer that there's likely to be rip currents there. And what you can also do is have a look at where the sandbank might be based on where there's a lot of wave breaking. So these are some quite useful tools in understanding coastal morphology. The other thing you can do is manage lagoon entrances. In New South Wales, we've got a bunch of these intermittently open and closed lagoon systems that local councils have to mechanically go out and open to reduce nuisance flooding for the houses that live around the area. And you're in a constant battle between residents that want to open the system versus nature that kind of wants to close them. And what's really useful with these types of time-lapse images is you can use them as a talking point when you're consulting with the community, because the timing of when you open up these systems is quite difficult sometimes. If you open them too early, you can let waves propagate into the entrance and make the flooding worse. You can see here, waves are propagating in. And if you open it too late, then you can get quite a bit of flooding of coastal communities. So these types of time, that community consultation. The final thing I'll show you with is a bit of a dashboard that we've developed to provide Central Coast Council with access to 9 cameras that we've developed and installed. So we've got a couple of different things that we present. We've got a time-lapse video that we generate every night to show them a month's worth of coastal change. We also host some local tide data and measured water level wave data from different sources to help them manage the lagoon entrance. And they can very easily just click between the different sites to look at a live feed from those cameras. If you're interested in this dashboard, reach out and I can send you a link to it. So I suppose that's kind of my presentation of the spectrum of coastal imaging techniques that are out there. On one hand, you've got a very sophisticated network that can do video-based analytics, or you can go for a much cheaper, low-cost system that's a lot more flexible, but still is able to give you some very useful information. So on that note, I'll stop talking and I'll hand it over to any questions that.
I'm having trouble with my sound at the moment. So Giovanni, do you mind doing the questions while I fix it?
I'll go ahead and start, in fact, with the question directly, as others will probably come through. What about inverting